Well, good evening, everybody. My name is Kevin Mace, and I'm very happy to be with everybody tonight. Welcome to our fourth live moon tour in this series. We are coming to you tonight live from the University of Texas McDonald Observatory Frank N. Bash Visitor Center. And as I said, my name is Kevin Mace. I'm part of our outreach team here, and we do not yet have a date for the reopening of the visitor center. It will reopen at some point. We don't yet know. If you want to stay abreast of when we do plan to open, make sure you stay tuned to our website, also to our social media channels. We will let you know about that information soon before we reopen. And once we do reopen, we hope to see some of you out here in person to take part in guided tours and star parties and other events here at the Visitor Center. I wanted to let everybody know that our next moon tour in this series is Tuesday, this coming Tuesday, June the 30th at 9 p.m. I have some good news and I have some bad news for everybody. Which do you want first, the good news or the bad news? I'm going to give you the good news first. We have a wonderful program to share with you tonight, and much like a normal program tonight, the bad news, if you can call it that, is that we currently have cloudy conditions. We did have a little rainstorm earlier, just a trace of rain basically. There's still a little bit of water dripping off the dome. I do have the dome closed. The telescope is turned off. And so we are going to do what we call a virtual moon tour tonight. When we get to that portion of our program, it will be very similar to the views that we get from our live telescopes, except that it will be data from the Lunar Reconnaissance Orbiter. That's the spacecraft that we talked about in our last program, the May 29th program, during which we talked quite at length about the Lunar Reconnaissance Orbiter and the amazing data that it's sending back to us here on the Earth. So we still have a full program for everybody. And as we do in all of our programs, I wanted to show everybody where I am located here tonight. You're currently seeing the summit of Mount Locke. That is the highest point on our campus here at an altitude of about 6,800 feet above sea level. You see two domes there on the very summit of the mountain. The larger of the two is the 107-inch Harlan J. Smith telescope. The one on the right, the smaller dome there on the summit, is the 82-inch Otto Struve telescope, which was the first telescope that was located here and dedicated on May 5th, 1939. If you look in the background there, you see on that more distant summit, that's Mount Fulks. That is our largest telescope atop Mount Fulks. That is our 10-meter Hobby Eberly telescope. That's the summits of our location here. I want to show you actually where I am this evening. I'm located in the dome that will soon be circled in yellow. It's right out behind the Frank N. Bash Visitor Center at McDonald Observatory. You can see we have a few domes out behind the building, enclosing a 16-inch telescope in this dome, a 22-inch telescope in the dome that you see just to the right of the one where I'm at, and then that little bit more distant white dome is our 20-inch telescope, most of which we have operating during our star parties. And like I said, we will reopen in the future and provide views from these telescopes for you. Wanted to give you a brief overview of the program tonight. The introduction, that's basically what we're doing right now. I'm going to show you the equipment that we're using tonight, both of the telescopes that we would have been using tonight if we'd had better conditions. We'll do a live tour. Well, I guess it's not really a live tour. That's a virtual tour of the moon's major features, the low power view that we would normally feature for you. Then we'll have a discussion session in the middle of our program tonight. Now, this is the part of the program that is different for every single live moon tour that we do. I try to pick out something interesting to talk with you about during our discussion section. And tonight we're going to discuss the gravity that you would feel standing on the lunar surface, and also talk about something called libration. Then we'll transition to our virtual tour of the high power moon, the one that we would have gotten through our 16-inch telescope tonight. We'll round out our program tonight with some Q&A. I did want to mention you should not necessarily wait until late in the program to ask your questions. We have moderators in the chat on the right side of your YouTube window there. You can ask questions of our moderators in the chat throughout the program. The moderators will select out some questions to relay to me, which I will answer at the end of our program tonight. And then I'll give you some resources to learn more about the moon. And then we will sign off for tonight until Tuesday. Next Tuesday at 9 p.m. is our next program. Now, this is a picture I took of the dome where I'm located on the last moon tour at the end of May. And I really wish our skies looked like that tonight. They don't. But that is the dome in which I'm located. You can see the dome open there. Inside that dome, we have a couple of different telescopes. You can actually see the back end of both of these telescopes here. The telescopes, two of them, the smaller one, the one that's right here, mounted on top of the main one, that is a 3-inch Teleview 76 short focus refractor or lens type telescope. That's the telescope from which we would have received our low power view of the moon tonight. Again, we will be simulating that using data from the LRO. The larger telescope that you see right here, including the cameras on the back end of the telescope, this is our 16-inch telescope. This is what's known as a reflecting telescope because instead of having a lens at the front end of the telescope, it has a mirror down at the bottom end, over here where I'm at. The light comes in, reflects off the primary mirror, reflects up to the top of the telescope, off of a second mirror, back down the tube again through a hole in that primary mirror, out the back of the telescope, and into a camera. The cameras we would have been using tonight are both cameras from a company called Point Grey Research. We have two different models of their camera. One is a 5 megapixel, the other is a 2 megapixel. And finally, the mount refers to the part of the telescope that allows the telescopes to move around north and south and east and west, and also to track as the Earth spins and causes the moon to apparently shift its position. It can do all of that. And we have a very, very beefy mount. It's from a company called Software Bisque. They are located in Colorado. And we have one of their mounts that's known as the Paramount ME. Now, as I do in every program, I always want to emphasize that you do not need a gigantic and hugely expensive telescope to get superb views of the moon. This slide you're seeing right here shows two of my telescopes. These are two of my recent acquisitions. They weren't in great shape when I got them, but I refurbished them. One, the red one that you see there, is a Tasco 4-inch reflecting telescope from the mid-1980s. Whereas the white one over there is a Mayflower Model 824 from the mid-1970s. Now, look at the red telescope. You see near the top there, the part that sticks up quite a bit, that is the eyepiece. And if you have a small telescope like this, there are devices that you can buy, shown there, mounted onto the eyepiece of my Tasco telescope, is the Orion Steady Pix. What it does is it clamps onto the eyepiece, and then you can put your camera. You see a camera there on the left side. That's a small point-and-shoot camera aimed directly into the eyepiece of that 4-inch telescope. And using that setup, I acquired the image of the moon that you see right down there below. So if you have even a small telescope at home, you can get great views of the moon. And if you have a way of holding your camera or your smartphone up to the eyepiece, you can take pretty amazing, at least low-power moon images. Speaking of which, let's go look at the moon. I want to show you our virtual view of the moon that we have tonight. And I'm going to turn off my camera view there for just a moment so I can get some other stuff going here for us. Now that says simulated moon view because this is not a live view of the moon. This is a view of the moon taken by a spacecraft called the Lunar Reconnaissance Orbiter. This spacecraft has been in orbit around the moon for about 10 years or so, and this view that you see precisely replicates the phase of the moon that we have tonight and the libration state. And we're going to talk about what libration is here in a little bit. But it completely reproduces our view of the moon tonight. And so this is very, very similar to the view that we would have had if we had a clear sky. Now look at that image of the moon. There's some things I want to point out for you. Let me get my little pointer on here. Notice that it looks roughest. The moon's surface looks the roughest along this line that you see right here. That line is called the terminator, and that is where the sun is rising. For a waxing moon, which we have now and for about the next 10 days or so, that terminator is where the sun is rising, and because the sun is coming in at a low angle to the surface, it accentuates even small terrain differences on the moon and makes those really show up a lot better. So the terminator right along here, it's not necessarily that the moon is rougher along the terminator, it just looks that way because of the light angle, the sunlight angle striking the moon. Did you notice those big dark patches on the moon? Like there's one over here, and there's one over here, and one in the middle. That's one you've all heard of before. We'll get to that in a little bit. We have another one over here and down here. These are known as the seas on the moon. Now, they're not filled with liquid water. They were once filled, however, with lava. There was volcanism on the moon in the past. We don't think there's any active volcanism on the moon today, but there certainly was in the past. And the lava's pooled up in those big dark patches, some of which are impact basins. Basically like a crater, like you're seeing the smaller craters on the moon there. The impact basins are just much, much larger versions of those smaller craters that occurred early in the moon's history. And I wanted to name a few of them for you. The round one over here on the edge is known as the Sea of Crises. This big one up here, roundish, we're just missing a little bit of it in the shadow over here. That one's known as the Sea of Serenity. The one in the middle that I said everybody knows the name of this one, that one is the Sea of Tranquility, the site of the first human landing on the moon, which we're going to talk about tonight in our high-power tour of the moon. Just a little bit over to the southeast of the Sea of Tranquility is the Sea of Fertility. And finally, the Sea of Nectar over here. So again, those are big lava patches, or at one time lava patches, now basaltic lava flows. Now, if they're not water, if they're not filled with water, why do we call them seas? Well, because a long time ago, before we had telescopes, people would look up at the moon as you can yourself, assuming you have a clear sky. You can see those big dark patches, and because they're darker, there's an obvious contrast between them and the rest of the moon, and you don't really see any detail out in the middle of those features. A lot of folks back then thought that they could be bodies of water, not unreasonably so. But, you know, Galileo and Thomas Harriot came along and looked at the moon for the first time and saw features out in the middle of those seas. And so we knew at that point they were not filled with water, but, you know, we've been calling them seas for so long, the name kind of stuck at that point. So we have the terminator, we have the seas, we have the craters. Now you can see the largest craters there, the craters that are bigger than probably about 25 miles are visible in this view. We're going to come back to our live view of the moon in a little bit, which will be a much more magnified view of the moon. But first, let me take you back to our slides, and we're going to go through our discussion session tonight. We have some moon facts up here I want to show you first. I show you these for every program that we do, things like the distance and the size, and the mass of the moon and the age of the moon. You can look these up on Wikipedia, do more research on your own. We're not going to go through all these. But this question is one that we get a lot here at the observatory. Back when we were open, we had a program, and we will one day have a program again, called our Lunar Twilight Program. We have twilight programs throughout the month on different topics, depending upon if the moon is up or not up. We have one about the solar system. We also have one about the moon. And during those moon programs, just about every program I would do, somebody in the group would ask, how much would I weigh if I were standing on the moon? So let's talk about that for a little bit. Now, I promise this is the only equation that you're going to see tonight. And in general, I don't want to throw a bunch of equations up there, but this one's particularly important because it describes the surface acceleration, the surface gravity that you would feel standing on an object. That's little g, and it's a function of a few things. G, capital G, is called the gravitational constant. It's just a number. M, capital M, is the mass, kind of like the weight, not really the weight, but sort of analogous to the weight of the object on which you are standing. And R there, R squared in the denominator, that is the distance from your position standing on the surface of that body to the center of that body. It turns out for a sphere, you can figure that all the mass of that sphere is located right at the geometric center of that sphere. Now, it's true the moon and the Earth are not perfect spheres. They have mountains and ocean basins and things like that. But when you compare the depth of the ocean basins and the height of the tallest mountains on the Earth, they really pale in comparison to the diameter of the Earth. Earth's 8,000 miles wide. So essentially, you can consider all that mass to be at the middle of the Earth or the middle of the moon. Now, the good news is, if you already know how much you weigh on the Earth, you can figure out how much you would weigh on the moon, given now m is a relative mass. It's the percentage of Earth's mass that the moon is, and r squared, r there in the bottom, is the proportion basically of the moon size to the Earth size. And you can see there the moon's mass and the moon's radius are listed there. So if you do all that and you run the numbers, it turns out that on the moon, if you weigh 100 pounds on the Earth, you would only weigh about 17 pounds on the moon. If you weigh 200 pounds on the Earth, then you weigh about 34 pounds on the moon. Now, your weight changes, but your mass doesn't. Your mass really is sort of like the number of atoms that you have. It's the total mass of all the atoms in your body is your mass, and that doesn't change. Unless you, I don't know, lose an arm on the way to the moon or something, your mass is not going to change. That remains constant regardless of which body that you're on, but your weight is related through the acceleration of gravity, that little g. Okay, so you can figure out now how much you would weigh on the moon in preparation for your going there, and that's a good thing to plan ahead. Now, I want to talk about something that gets a little bit down in the weeds, but it's something that lunar observers notice. It's not really something that you would notice with your naked eye looking at the moon. But if you have a telescope and you do lunar observations, the appearance of the moon is not only affected by the phase, but something else as well. And I want to show you something really cool here. This is how the moon would look to you on the Earth if it did not go through phases. If the side facing you on the Earth was fully lit all the time, if the moon was full all the time, and you looked up at the moon over a period of time, you would notice it sort of wobbling like that. You see how it's wobbling back and forth? This wobbling is called libration. Now, there is a different sort of wobbling that can be induced by a libation, but that is a separate program. We'll talk about that on a future date. But libration describes how the moon appears to wobble over an orbit of the Earth if it were full all the time. It basically reveals certain parts of the moon sometimes that you would not ordinarily see. Now, notice that as the moon wobbles there, it's wobbling both up and down. That's called a libration in latitude. It's sort of going like this. It's also wobbling back and forth like that, which is called a libration in longitude. It's doing both of those separately at the same time, producing this sort of complicated wobbling motion. Let's talk about why this happens. Let's talk about first libration in latitude, that up and down bobbing of the moon. It's a little bit easier to understand the latitude component of this than the longitude component of this. Libration in latitude comes from the fact that the moon's axis of rotation is tilted with respect to its orbit around the Earth. Now, in the graphic here, I have the moon tipped over more than it actually would be. The real tilt of the moon is only about 7 degrees compared with the orbit of the moon around the Earth. And the libration latitude comes from the fact that, say, for example, over there on the left where you see southern libration, it's the southern axis of the moon that is tipped a little bit toward the moon or toward the Earth. So we can see a little bit under the southern part of the moon and see regions that on average we don't see. If you look over there on the right, you can see the northern libration, now the northern axis. The northern pole of the moon is sort of tipped toward us on the Earth, and we can see features near the lunar northern pole that we would not normally see. So libration in latitude simply comes from the orientation of the moon in space with respect to its orbit around the Earth. Now let's talk about, let me show you this first. I forgot I had this in here. I have an example here of a libration in latitude, a favorable southern one there on the left, and a favorable northern one on the right. Now let me get my little pointer on because I want to show you what I'm talking about here. This favorable southern libration, you notice that really prominent crater right there? That's called Tycho. Tycho crater, named after a Danish astronomer, a pivotal figure in the history of astronomy. He got pretty much the most prominent crater on the moon named after him. Now look at Tycho on the left and notice that you're seeing quite a bit of space between Tycho and the southern polar region, more space in here than you're seeing over here in this view. Now conversely, over here, for example, the crater Plato that we're going to talk about on Tuesday night. Be sure and tune back in. It's one of my favorite craters. Notice how Plato, for the favorable northern libration, has quite a bit of space in here, whereas over on the other image, you don't have as much space. So the effect of that libration is to bring more northern, more southern parts of the moon in view for the latitude component. Now, let's talk about the more complicated one, the libration in longitude. The libration in longitude comes basically from two things. It comes from the fact that the moon spins at a constant rate. And we've talked about this in prior programs, namely that we see one side of the moon because it spins on its axis in exactly the same period of time that it orbits around the Earth. So we can only see that one side. Well, turns out because of libration, that's not quite true. We can see about 59%. But libration and longitude comes from the fact that the moon spins at a constant rate, but the orbit of the moon around the Earth is not a circle. It is an ellipse. And because it's an ellipse, and the ellipse I've shown here in this graphic is greatly exaggerated from the actual amount that the moon's orbit is elliptical. I've exaggerated here just so we can kind of visualize what's going on. So because the moon spins at a constant rate, it goes around the Earth on an elliptical orbit, it's moving faster when it's near the Earth. It's moving faster at that point called perigee, labeled in green. Whereas the moon is moving more slowly along its orbit over on the long side of the orbit near apogee. Now there's a few things going on here. This little arrow right here and the other arrow up there on the other moon, that indicates the direction of rotation of the moon. All right, so looking down on it, it's rotating counterclockwise, same direction as the Earth rotates. Now, because the moon spins at a constant rate, but it's moving faster near perigee, basically what that allows us to do is to peek around this eastern side of the moon a little bit, because essentially the moon is sort of spinning more slowly with respect to how fast it's moving around the Earth shortly after perigee. And so we can peek around this eastern side a little bit versus half an orbit later, more or less, the moon has moved over here past apogee, still rotating in the same direction, but because now the motion of the moon around the Earth is slower, rotation speed is still the same, that means it's getting a little ahead of itself in the rotation. And so we can see a little bit around the western side of the moon. I know it's a little complicated. We're getting a bit down in the weeds here, but it does produce a very observable effect when we look at the moon. Now, here's that same example, except this time for longitude. And a good indicator for a good western libration is this crater right here called Grimaldi. That big dark patch near the western end of the moon, Grimaldi. Look how you've got a fair amount of space here at a good western libration, but not as much over here. Conversely, look at the Sea of Chryses, one of the seas we looked at tonight. This is a good eastern libration, so you got a bit more space over here than you do over here. And so you add up the effects of libration and longitude and latitude, and that means in total we can see about 59% of the moon's surface over a period of time. All right, well, it is time for us to do some serious observations of our moon. We're going back to the view that we had earlier when we were looking at the low power moon, talking about the seas and the big craters and the terminator and all that. And what I'm going to do now is zoom in on this image. We're going to zoom in just a touch more than that. And now we're going to go up to the top. We have 4 parts of the moon that we're going to talk about tonight, 4 fields of view that I want to discuss with you. We're starting here near the north pole of the moon, the northern section of the moon, and let's see, let me get my little descriptors up here. Look over there on the left side of your screen. You see that low power moon that we saw earlier. That small yellow rectangle indicates the proportion, the amount of the moon that we're seeing compared to the whole moon. What we're seeing in the little yellow rectangle on the left is our field of view there on the right. And we're going to talk about a number of features here. And we begin our program tonight welcomed by a familiar pair of craters called Aristoteles and Eudoxus. Let me point out those for you. These are craters that we've talked about before. This is Aristoteles crater, and this is Eudoxus crater. The larger of the two craters there that you see, the northern one, is Aristoteles, and it spans 54 miles across, while Eudoxus clocks in at 42 miles. Both are over 2 miles deep, and so they appear to be bottomless in this view because of their close proximity to the terminator at this point in the lunar day. The sunlight basically has just not yet reached their floors. It will in the next few days. Now, asteroid impacts over the span of billions of years have left their marks all over the lunar surface. The size of the asteroids that formed our pair of craters is unknown, but they were probably in the range of between 2.5 and 3 miles. These projectiles travel at speeds between 25,000 and 160,000 miles per hour, so they really leave an impressive mark when they hit. Impacts do still occur on the moon today, but thankfully the impactors are much smaller. Now, the low sun angle reveals a somewhat rough blanket of material surrounding Aristoteles' rim. All this stuff that you see just outside and particularly up here along the northern side of Aristoteles. This feature that you see here is known as an ejecta blanket, and it represents material ejected out of the crater when it formed. Basically, asteroid comes in, excavates a large crater, stuff flies out in all directions, but some of it just plops out right outside the crater, and that's called the ejecta blanket. Now notice this general dimpled texture that you're seeing in through here. Let me point out what I'm talking about. All this kind of stippled appearance of the moon there. This is part of an ejecta blanket from an older, larger lunar impact that produced the Imbrium Basin. Now, we cannot see the Imbrium Basin this early in the lunar day, but if you come back on Tuesday, it's going to be very visible. The dimpled surface surrounding our dynamic duo of craters there is called the Alps Formation, and it represents coarse rocks measuring hundreds to thousands of feet across that rain down on the lunar surface during the Imbrium impact. Now, over greater distances, Imbrium ejecta transitions into a fine blanket of pulverized rock that partially fills the interiors of older craters and levels the landscape between them. Geologists call this fine deposit the Cayley Formation, and together it forms the Imbrium Plains. Now look out near the top of the moon, just a little bit north of where we're looking here. Up in this region, also the craters Atlas and Hercules over here. Notice that they're somewhat subdued, and they're subdued compared to their lofty southern hemisphere counterparts. They're basically the same age as those other craters, so why the difference in appearance? Well, as they say in real estate, folks, location, location, location. Ejecta from the nearby Imbrium Basin greatly soften this once impressive part of the moon. Lava began erupting in earnest on the lunar surface, by the way, about 3.9 billion years ago, around the time of the Imbrium impact. The dark, smooth plains we see on the moon today, that we mentioned earlier, are called the seas, or the mare, and they are vast fields of basaltic lava. Look above the craters Aristoteles and Eudoxus. There's another one of those dark plains up here. I wanted to point that out to you. This region is known as the Sea of Cold, or Mare Frigoris, and it spans about 1,000 miles from east to west in the northern part of the moon up there. Former Sul Ross State University planetary geologist Dr. Jim Whitford Stark estimated that the Sea of Cold covers about 200,000 square miles and is filled to a depth of greater than 1/4 of a mile. Now, some of that lava flowed into a low depression east of Aristoteles and Eudoxus to form one of my favorite named features on the moon. We're talking about this little dark patch right in here. This is called the Lake of Death. I just love that, the Lake of Death. Now, Dr. Whitford Stark estimated that its coverage at about 21,000 square miles. Let me get my pointer out of the way here because I want you to notice that the lake margin is not raised like a crater rim, nor is it circular or oval, but instead appears somewhat hexagonal. Dr. Charles Wood with the Planetary Science Institute says linear structures like this are found all over the moon and are commonly related to either basins or tidal stresses that developed when the moon was much closer to the Earth in the distant past. This crater, by the way, out in the middle of the Lake of Death is called Berg, B-U-R-G, Berg crater. It measures about 39 miles across, is 1.9 miles deep, and has a nice central peak rising up to about 1 mile in height. That's a pretty impressive part of the moon. I wish that we had had a clear night tonight. It would have looked basically like what we're seeing here, but there's always something nicer about seeing the live moon. Okay, now we're going to proceed southward in our virtual view of the moon here, and this is, of course, much easier using the virtual moon than using the real moon, if I can figure out how to do it. There we go. And we're going to go down here a little bit, south of where we were before. I want to make sure I've got things centered up about the way I need them to be. Yeah, that looks good. This is our second field of view on the moon here tonight that we're talking about. Let me see. I need to do one more thing here for you. Put up our next series of slides. There we go. Notice that little yellow rectangle has moved down. Now it's showing that smaller part of the moon there that we're seeing on the right. Our next view takes us down the terminator into the Sea of Serenity. That's the big circular dark patch that you see there, filling most of the view there except near the bottom. The Sea of Serenity, also known as Mare Serenitatis. This sea measures 439 miles in diameter, and according to Jim Whitford Stark, it covers an area of 220,000 square miles. The sea rests inside of an ancient impact basin named after the mare that resides in it, the Serenitatis Basin. The basin is about 572 miles in diameter, is about 1.33 miles deep, and has a strong positive gravity anomaly that indicates that a large impact occurred there. Lava began to fill this basin in the Upper Imbrium time period, about 3.8 billion years ago, and concluded about 800 million years later. Basaltic lava flows are very, very dense, and these thick deposits have caused the center of the basin to sink. This has resulted in the formation of a number of shallow thrust faults that have compressed the surface into a series of low ridges, sinuous ridges, known as wrinkle ridges or dorsa. I want to point out what I'm talking about here. That all sounds geologically interesting, but what are we talking about? You probably already noticed them. This long ridge that you see here, continuing on up. You also see further examples of the same sort of thing over here on the western side of the Sea of Serenity. Now, the first one I pointed out here for you, this one, that one for years was known as the Serpentine Ridge. In recent years, however, the term Serpentine Ridge has been abandoned in favor of the usage Dorsa Smirnov for the northern branch. It's basically this section of it right here is Dorsa Smirnov, and Dorsa Lister for the southern curving branch that terminates near the small deep crater Bessel. So Dorsa Lister starts about here, loops up around, and terminates near Bessel. Bessel crater, by the way, is about 10 miles in diameter and about 5,800 feet deep. South of the crater Bessel, you probably already noticed it. I did not mean to do that. Let me do this. Right in here. South of Bessel, we have a curving chain of mountains that form the southern margin of the Sea of Serenity. These mountains are known as the Highlands Mountains. They extend about 300 miles along the Sea of Serenity, and some peaks reach elevations of about 8,000 feet. The grooved appearance was, as it turns out, a byproduct of those blocks of rock that scoured the lunar surface during the Imbrium impact event 3.85 billion years ago. You see how there's sort of these gashes, these tears almost, it looks like, in the lunar surface. That was caused by ejecta flying away from the Imbrium impact, which is northwest of where we're looking here. But now let's turn our attention to the eastern shore of the Sea of Serenity. Here we dry off in the light-colored, heavily cratered ancient lunar highlands and home of the Taurus Mountains to investigate the landing site of Apollo 17, which touched down right about there. And I want to show you a really cool Lunar Reconnaissance Orbiter fly-around of this part of the moon. This is known as the Taurus-Littrow Valley, where you see Apollo 17 marked there. Straddling the boundary between the Sea of Tranquility's northern shore and the eastern margin of the Sea of Serenity, this Taurus-Littrow Valley, as it's known, hosts a number of geologically interesting features. This region represents part of the eastern rim of the Serenitatis Basin. Sections of the lunar crust, uplifted during the impact, form a series of isolated hills known as massifs. The age of the basin has been debated for years, and it was hoped that samples would pin down its exact age. Also, there were other notable features in this area, including a landslide, a thrust fault, and a young deposit of dark volcanic material on the valley floor. Okay, let me take you back to our live moon view here. Apollo 17, that marked there at the tip of that finger, I got just as close as I could get it there. Apollo 17 is the easternmost of all the Apollo sites and one of the most challenging to land in. Why, you ask? Well, the Apollo landing window on the moon starts at 34 degrees east of the lunar meridian. That's basically the center line of the visible moon that we see from Earth. That's the meridian of the moon. And the landing site of Apollo 17 was just barely 3 degrees beyond that point. When Apollo 17 astronauts Gene Cernan and Harrison Schmitt came around the lunar far side to begin their descent to the lunar surface on December the 11th, 1972, they only had about 15 minutes of communication with Houston to determine their orbital position prior to landing. That's pretty cool. Needless to say, they were successful. And during their 75 hours spent on the surface, they conducted 3 EVAs, that's technobabble for extravehicular activities, and collected 244 pounds of rock and soil samples, including orange volcanic glass. Some of the oldest samples include deep-seated rocks that formed at the base of the lunar crust over 4.2 billion years ago and were uprooted by ancient impacts like the Imbrium event. Serenity lavas at the Apollo 17 site were dated at between 3.7 and 3.8 billion years old, and those are also similar to Apollo 11's landing site. The orange glass collected on the second EVA erupted from what's known as a fire fountain 3.64 billion years ago, tapping a deep-seated magma source at least 250 miles below the lunar surface. That, for me, is one of the most photogenic landing sites of all of them. The Apollo 17 landing site, also the last of the human landings on the moon that concluded back in the early 1970s. Now we're going to venture a little further south in our high-power view of the moon tonight, and we're going to go down along the terminator, and we're going to see a number of things in this view as well. Make sure I'm getting it centered right about where we want to be. Yeah, that's pretty good. All right, now we have moved south and entered the Sea of Tranquility, also known as Mare Tranquillitatis, site of the first human landing on the moon. The Sea of Tranquility covers 271,000 square miles. according to measurements of Dr. James Whitford Stark. And its high titanium lavas are about 3,300 feet thick. The Sea of Tranquility is sort of unique because it does not occupy an impact basin like most of its surrounding neighbors, surrounding seas. Now look at the terminator right along the edge of the visible part of the moon. I want to direct your attention to this crater right here. That is the tattered remains of a crater known as Julius Caesar, named for the once emperor of Rome about 2 millennia ago. This crater is 56 miles wide, about 4,200 feet deep. The crater wall has been extensively eroded and cut down by flying ejecta from other impacts. East of Julius Caesar is the irregular crater Arago, which is this one right here. And I want to show you something that's a little bit subtle. I'm looking really closely at our LRO image here. Yeah, I can see that. Look right here at the tip of the finger, a little bump on the surface, one right there, and then there's another one right there. You see those? Those are these two faint ground swellings north and west of the crater. These are low mounds or lava domes, basically low-profile volcanoes that once erupted onto the moon. As I said earlier, as far as we know, there's no active volcanoes on the moon today, but there definitely was in the past. This is sort of a low-level volcanism on the moon long ago. East of Arago, there's a faint circular outline of a ghost crater called Lamont. This is also a bit subtle. Basically, it's this region right in here, just shadows, basically, of the walls of an ancient crater. Now, before lava began to fill the present-day side of the Sea of Tranquility here, the surface probably looked like the lunar Highlands, north of Apollo 17's landing site, where we looked previously. Floods of basaltic lava, though, erupted between 3.6 and 3.8 billion years ago, burying the former landscape underneath thousands of feet of molten rock. Eventually, only the rims of a few pre-existing craters protruded through the flows, while others were submerged, forming faint circular structures known as ghost craters like Lamont. Look down below where we saw Lamont there. Down here we have a pair of craters. Those are the twin craters, Ritter on the left and Sabine on the right. Ritter and Sabine are both 19 miles in diameter. East of Sabine, we find the landing site of Apollo 11 near the southern shores of the Sea of Tranquility. When I'm looking for that landing site, I always look for this little semicircular feature right here, and then this really small crater, that's a 4-mile wide crater called Moltke. Moltke. This is the landing site, landing area, which is specifically right about there, where Apollo 11 set down. Commander Neil Armstrong and lunar module pilot Edwin Buzz Aldrin successfully landed their spacecraft, the Eagle, on July 20th, 1969, while Michael Collins piloted the command service module Columbia in lunar orbit. Did y'all know, though, that 2 months earlier, Apollo 10 astronauts, Tom Stafford and Gene Cernan, had brought the first lunar module, named Snoopy, to within 10 miles above Apollo 11's landing site as a full dress rehearsal in preparation for the actual landing. Armstrong and Aldrin were on the surface for a mere 21.5 hours, of which 2.5 hours were spent outside the Eagle, photographing the surface, deploying experiments, and collecting about 48 pounds of rock and soil. One of the instruments placed on the moon was a laser retroreflector. McDonald Observatory has performed lunar laser ranging for decades now with this device and 3 others, one of which was delivered to the moon by a Soviet unmanned rover. That's pretty awesome. Now, while I'm setting up for the next view, I want to show you an equally awesome fly around, again from the Lunar Reconnaissance Orbiter, showing the Apollo landing site, Moltke crater, that little semicircle feature below Moltke there south of it, and 3 small craters named after the first astronauts that journeyed to the moon, 2 of whom walked on the surface. And while you're enjoying that, I'm going to get set up on our final field of view tonight. This will be a short one compared to the last one. Our third field of view tonight was by far the longest. But I'm getting set up here. I want to show you, yeah, that looks about right. Okay, let's go back to the moon. Now we've entered our final field of view for this evening. We've gone further south and encountered the Sea of Nectar, Mare Nectaris, in the upper right corner of our image. And where I'm looking, describing as this circular feature right up here, that is the Sea of Nectar. Now, just as we saw with the Sea of Serenity, Mare Nectaris rests inside the basin for which it is named. The impact that formed this basin 3.92 billion years ago also heralds the beginning of the Nectarian system in lunar history, which extends from 3.85 to 3.92 billion years ago. This 535-mile wide multi-ringed basin is the product of a roughly 30-mile diameter asteroid impact. The collision excavated about 3.5 miles of the lunar crust vertically. During the early Embrian period in lunar history, the central over 200 miles of this basin was flooded with about 1/2 mile of basaltic lava. And again, the weight of the lava caused the lower density highland crust below to sag downward. And one indication we have of that, this is a crater we've mentioned before, this crater right here is known as Fracastorius. And notice that it has a nice western and southern and eastern rim, but it's missing its northern rim up here because as the basin, once filled with lava, pushed down, compressed the surface, the basin-facing side of that large crater, Fracastorius, was tilted inward and then subsequently filled with lava. Another crater that we've talked about before, down here, 87 miles south of Fracastorius, we see the 54-mile wide crater Piccolomini and its 7,350 foot tall central peak. This crater was named for the Italian philosopher Alessandro Piccolomini. He promoted the use of Latin and Greek scientific terms. Piccolomini lies at the end of a roughly quarter circle escarpment known as the Altai Scarp. Let me show you what I'm talking about. You probably already noticed that. It's pretty obvious over there. That is known as the Altai Scarp, and it is part of the preserved rim of the Nectaris Basin. And it can be traced across the surface for about 265 miles and includes a maximum elevation of about 3,300 feet. At about the point where the western part of the Altai Scarp, this section over here, terminates, we can see 3 similarly sized craters in vertical succession. And from top to bottom, we have Theophilus, Cyrillus, and Caterina. Now, Theophilus up here is the youngest of the trio and thus the best preserved. It is named for Saint Theophilus, the Bishop of Alexandria, Egypt, in 385 AD. The crater is 68 miles in diameter, and its central peak, split into 3 parts, rises about 4,600 feet above the floor. Theophilus' southern wall, as you've probably noticed here, overlaps the northeast wall of an older crater called Cyrillus. Cyrillus was the bishop of Alexandria who succeeded Theophilus. This battered crater has a diameter of 61 miles and sports a trio of unequally tall central peaks. Now, the oldest crater, at the bottom of our trio right down here, is the crater that is known as Caterina. Saint Caterina was another resident of Alexandria, Egypt, except that he died about 80 years before Theophilus became bishop. Caterina probably formed just after the Nectaris Basin, and so its 65-mile diameter and 1.9 mile depth have been greatly softened over the eons because of the filling of ejecta from earlier impacts. All right, we are just about done, folks. I'm checking my time here. We need to be just about done. I'm going to switch back to our low-power view, which for this virtual view is just a single keystroke once I can get my act together here. Let's see if we can make, there we go. Let me turn off the little pointer. I wanted to leave this image of the moon up here, and we're going to do our Q&A here in a minute. I just wanted to point out that although that was the last part of the moon that we're going to talk about in depth, now that we're on the low power view, you can see where we were. And let me show you specifically where we were in the last view. Okay, here's Theophilus, Cyrillus, and Katerina down here. South of this area, which we're not going to talk about in depth tonight, but basically this is the seemingly carpet-bombed landscape of the ancient southern lunar highlands. Most of the craters here formed in the Nectarian and pre-Nectarian period, so they are among some of the oldest features on the lunar surface. Deposits from the Imbrian Basin did not really affect this area much because they're very far away from that area. And so the craters here are not as subdued compared to those in the northern regions of the moon, closer to that Imbrian impact site that we mentioned earlier. Now, in future programs during which we have favorable southern librations, and I can use that word now that we all know what it means, we will further investigate the lunar southern polar area. For tonight, however, that wraps up our high-power tour of the moon. And now I would like to take some of your questions, which were forwarded on to me from our social media team, from our moderators in the stream here tonight. And let me see, I need to turn a few things off, turn that off, get me back up on the screen. I'm just going to leave you with that amazing low-power view of the moon. Let me go over here to my list of questions from the internets. Let's see. Ramesh says, it does look like the dark side of the moon from Earth perspective is more cratered. Any specific reason? Yes, Ramesh. Now, I must say first, there actually is no such thing as the dark side of the moon. I know what you're referring to. You're referring to the other side of the moon. That side gets just as much light as the side that we see over a full orbit of the moon around the Earth. We generally call that the far side or the other side or something like that. But I know what you mean. Basically, why does the other side of the moon look more heavily cratered? It does look more heavily cratered, mostly because of the absence of those seas. There's only one sort of kind of major sea on the backside of the moon, and it's because of the absence of other seas that you see more craters. In other words, if you took the front side of the moon, the side that we see, and you subtract away the seas, the lava flows that occurred from major impacts in the past, if those were not there, then the Earth-facing side of the moon likely would look very similar to the other side of the moon. It's only because the side facing us has more seas. Now, there's other things going on here. The crust is thinner on the Earth-facing side of the moon. It's thinner by a factor of well, it's half as thick. And we don't know exactly why that's the case, but that would allow the lavas coming from lower regions of the moon to more easily make it up if it didn't have to go through so much crust on the moon. So that is why that other side of the moon looks so much more heavily cratered. Let's see. Stephen Yanakasawa says, are there any natural satellites that orbit the moon? Periodically, yes. Things can wander into orbit around the moon. Since you asked that, I'm thinking back to something I read not too long ago, and I don't remember if this was an interloper natural satellite orbiting the Earth or orbiting the moon. But basically, yes. Small objects can be captured by the moon's gravity, but it's not really a stable situation because of the presence of the Earth. And it can be around the moon for a little while, typically on a very weird orbit, but eventually that small natural object is going to get ejected from the Earth-Moon system as it interacts with the gravitational force between the Earth and the moon. So there you go. Let's see. Joe Virgil says, what is the most recent meteor crash on the moon that we know of? Well, as far as we know, there are no impacts on the moon that have major impacts on the moon that have been seen throughout human history. Most of the heavy cratering on the moon stopped many billions of years ago. And so what's hitting the moon today is small debris that would not leave a visible crater visible, from your backyard telescope. Now, the Lunar Reconnaissance Orbiter has spotted very small impact craters on the moon that are fresh. We know that because it's been in orbit around the moon for about 10 years. And so it can go back and look at a region later that it had imaged before, and it has noticed very small craters impacting the moon. So yes, there are things hitting the moon, but not major things that mostly occurred many billions of years ago. Let's see. My final question tonight that we have time to cover is from Austin. Austin Padayo. Forgive me if I'm mispronouncing your name. What elements have we found on the moon? What elements have we found on the moon? If you look at the composition of the moon, and we know the composition of the moon very accurately, at least in regions where we've landed on the moon, and we've covered a pretty broad range of terrain on the moon where humans have landed, brought material back to Earth, analyzed that material in a lab. Fairly representative areas on the moon, all on the Earth's side, have been sampled. And what it turns out is it's very similar to the Earth's crust. So things like aluminum and some iron and oxygen and silicon and sulfur, a lot of the same things out of which the Earth's crust is formed is also present in the moon's crust. And this goes back to something we think formed the moon, which is an early impact of an object hitting the Earth, mixing material between that object and the Earth, that debris reforming in or forming into a moon, which would then have had at least similar composition to what we see here on Earth. So thank you all for your great questions tonight. I did want to remind everybody we will be doing another moon tour on the 30th. That's next Tuesday at 9 p.m. Positive thoughts for a clear sky on that night. Before we go, I did want to, as I always do, give you a few resources. Areas of research, you can go and learn more about the moon. I have read the Wikipedia Moon article several times in the last couple of months because prior to starting up our moon programs, our lunar twilight program several years ago, I'm an amateur astronomer. I mostly observe things that are not the moon. Deep sky objects like Stephen Hummel likes to look at during his deep sky tours, galaxies and star clusters and nebulas and all that kind of stuff. And honestly, I was not all that familiar with the moon, and so I had to learn a lot about the moon. And that Wikipedia article is a very good resource for you. In addition to Stardate magazine, Stardate Online has very good information, up-to-date current information about what planets are in the sky, articles, research articles in the magazine. Definitely encourage you to check that out. And finally, again, I wanted to thank all of you for joining us tonight. We very much depend upon your support for keeping these programs going. Again, we do not know yet when we will reopen. We hope that will be reasonably soon as it is safe to have people on site. We will have you here joining our programs. And please join us on Tuesday night for our second and final moon tour of the series. I'm Kevin Mace, and I will see everybody on Tuesday night. Thank you all very, very much. We appreciate it.